Up to this point, we've spent a good amount of time finding the derivative of functions, mainly to calculate the rate of change for those functions. Now suppose that we have a function that measures how fast a population of bacteria changes, but we want to find the size of that population in the future. In this case, if we can find an antiderivative for the rate of change function, we can calculate the population size. The first thing we want to do is define what we mean by an antiderivative. So we say a function capital F is called an antiderivative of a lowercase f on some interval I if the derivative of capital F is always equal to the lowercase function for all the x's in that interval. So that makes capital F the antiderivative of lowercase f. Now, for example, we know that 2x is the derivative of x squared. So we say x squared is the antiderivative of 2x. Now, the antiderivatives are not unique. 2x is also derivative of x squared plus 1, or x squared plus 3, and so on. And that gives us the following theorem. A function f is an antiderivative of lowercase f on that interval. Then the most general antiderivative of f on that interval is capital F of x plus some arbitrary constant c. Right? And that constant c could be any number, because when we take the derivative of it, it would disappear. And it doesn't matter what that value is for us to get lowercase f. Right, so let's look at an example. So we want to know what's the most general antiderivative for cosine of x. Well, we know cosine of x is the derivative of sine of x. That means the most general antiderivative of the function cosine of x is a function sine of x plus c, right? And again, c could be any number. And when we take the derivative of sine of x plus that number, we just get cosine x. Right, so that brings us to some anti-differentiation formulas based on all the derivative formulas we've already seen in the previous sections. So we know that when we multiply a constant times a function and take the derivative would have that constant just multiplied in front. So that would also work for antiderivatives. We know when we take a derivative of the sum of two functions, we just add the two derivatives together. So that would also work for antiderivatives. And we know when we take a derivative of a function of x to a power, we would subtract 1 from the power and multiply by what the old power used to be. So for x cubed, it would have 3 times x squared. Means when I take the antiderivative, I need to do the opposite. I need to increase the power by 1 and then divide by that amount. This works only when n is not equal to, it only works when n is not equal to -1. So when we have -1, first of all, notice this would become undefined, because on the bottom, I would have -1 plus 1, which is 0. But also, because when x is negative, when the power is -1, I have x to the -1 power. X to the -1 power is the same as 1 over x. And we know that 1 over x is the derivative of natural log of x. So the antiderivative of x to the -1, or 1 over x, is a natural log of an absolute value of x. And we need the absolute value because if x is a negative number, then the antiderivative would have been undefined. Right, so we do need the absolute value. We know that the derivative of e to the x remains e to the x, so the antiderivative would remain the same. And we knew if I took a derivative of e to the cx, I would get e to the cx times c because of the chain rule. Therefore, the antiderivative would be e to the cx now divided by c, or multiplied by 1 over c. And here are some other derivative that we had seen. We know the derivative of a sine x is cosine x, therefore the antiderivative of cosine x would be sine x. We know the derivative of cosine x would have been negative sine x, which means the antiderivative of sine x is going to be negative cosine x. We knew the derivative of tangent x is secant squared, therefore the antiderivative of secant squared becomes tangent. We know the derivative of secant is secant x tangent x. That means the antiderivative of secant x tangent x is going to be secant x. And finally, we know the derivative of tangent inverse of x is 1 over 1 plus x squared. Therefore, the antiderivative of 1 over 1 plus x squared is tangent inverse of x. So if we go back and look at all the derivative formulas, with a little bit of work, we can find all the antiderivatives from those. So next thing we're going to do is define what a differential equation is and look at an example of how a differential equation helps us solve some of the problems we had to deal with in the past. So a differential equation is any equation that involves the derivative of a function. Right? So I have an equation, it involves the derivative of the function. We call that a differential equation. Now we'll learn more about these in the future chapters, but for now we're just going to look at some elementary differential equations. Right? The general solution involves some arbitrary constant. If we are given enough information, we may be able to actually find that constant. Right? So the most basic one is the one we have on the slide here. We have an equation of the form dy dt or y prime is equal to some function. And that's what we call a pure time differential equation. Right? So you just have a basic derivative on one side of the equation, and on the other side I have a function that's independent of y. It only depends on variable t, which in this case represents time. It said the solution will be a family of antiderivatives. The initial value of the solution, right? So if this changes, if I could find at some point what the value is, we call that the initial condition. And we would have something of the form y equals y sub 0 when t is equal to t sub 0. And the problem of finding a solution of this differential equation, as long as I have some condition given, is what we call the initial value problem. Right? So if I have a differential equation, and for now we only look at pure time differential equations, and I have some initial value, I should be able to get an equation, find its constant, and then use that to calculate values I need. So here's an example. So we know that the rate I at which people are becoming infected with HIV, right? So we call that the incidence in New York in early 1980s, right? So we have data on an annual basis, how many people are infected with HIV, and here's the graph. And these dots represent the infection rates, and it looks like it's a pretty linear model. We can do a little bit of regression on it and actually find the best fit line that goes through it. And that equation turns out to be 16 plus 242t. Right, so that's the equation of that red line. And t is measuring the number of years since 1982. Right, so that's the first incidents that were recorded. So we're starting at 1982. Now, suppose that there were 80 infections in the year 1982. So this blue dot represents 80 people. And we start at t equals 0. So t equals 0 corresponds to 1982. That's our first reading. We want to know what's the number of infections expected in 1990. The prevalence of the virus in 1990. Okay, so what we're going to do is first start with a model. Since I was the change of the population, the change in the number of infected people in the population, we can start by taking I and calling it dp over dt. And that was given to be 16 plus 242t. Right? And we were told that in 1980, when t was 0, the population, infected population was equal to 80. So we have, that's our initial value. P of 0 is 80. Right? So if I go ahead and find the antiderivative, instead of dp over dt, we can find the population P of t is equal to 16 times t, that's the antiderivative of 16, right? So the 16 is the derivative of 16t, plus 242 times the antiderivative of t. And then the derivative of t is t squared over 2, right? We saw that we add 1 to the power and divide by it, the opposite of taking the derivative. And again, we can check the derivative of t squared over 2 would be 2 times t over 2, which is just t, plus a constant c. Right? And we can simplify this. 242 times t squared over 2 can become 121, just reducing 242 and 2. So now I have a general equation for the population. Next thing we got to do is try to find out what the constant is, c. Right? And then we're going to use this initial value to do that. Since we know P of 0 was 80, I can go ahead and plug in 0 for my t and set that equal to 80. I'll get 16 times 0 plus 121 times 0 squared plus c is 80. And 16 times 0 plus 121 times 0 squared happens to be 0. So I get 0 plus c is 80, which gives me the value of c. So in this case, c is equal to 80. And I can go back and rewrite my equation in a specific format with the c in it. Right? So 16t plus 121t squared plus 80. Right? So now I can answer the question they had asked me. They had asked me, what is the population in 1990? Or what was the population in 1990? Well, since we started with t equals 0 in 1982, 1990 would correspond to t equals 8. Right? So that's 8 years from the day we started our model. So I can find the population in 1990 by plugging 8 in for my t. So P of 8 is 16 times 8 plus 121 times 8 squared plus 80. And if I work all of that out, I get 7952. So in 1990, based on this model, there were 7,952 people infected in New York.